Hey guys, welcome back for another chemistry lesson. Today's lecture is going to be on mixtures and partial pressure. So up until this point we've been talking about gases as if it was just one kind of gas, but that is almost never the case. So we need to talk about gas mixtures and what we can do with those. So let's start with that. Most gas samples you'll come across, unless you're working in industry usually, are not pure gases, but mixtures of gases. So for example, you can see here that dry air, whatever you're breathing, has many different gases in it. These are just the majority components, but there are also traces of all sorts of other things. Carbon monoxide, methane, you name it, it's probably in the air somewhere. But this mixture has a certain kind of behavior that we can look at and still use all of the other gas laws that we've talked about previously. So in certain applications, we can think of that mixture as just a single gas. So even though air is a mixture, we can measure the pressure, the volume, the temperature of air like we have a pure substance. And then going from there, we can calculate total moles of molecules, even though they are different molecules. So the pressure of a single gas in a mixture of gases is called that gas's partial pressure. So for example, in the air that we're breathing, the oxygen creates its own pressure, and that is the partial pressure of oxygen. Likewise for nitrogen, carbon dioxide, etc. And so we can calculate the partial pressure of a gas if we know the fraction of the mixture it composes and the total pressure, or if we know the total number of moles in gas in a container, and then we know the volume and the temperature. All right, so when we have the partial pressures for all of the gases that we're looking at, we can then add them all together to get our total pressure. So again, thinking about air, we have nitrogen, we have oxygen, we have carbon dioxide, etc. And once we get the partial pressures for all the pieces, we can just add them together to get our total. Right? So this is called Dalton's law of partial pressures. And it allows for the fact that our gases behave independently, but we can still look at them as a whole group. So again, the pressure due to any individual component in a gas mixture is its partial pressure, and we can calculate that using the ideal gas law if we just rearrange by assuming that each gas component acts independently. So PV equals nRT, rearrange it to get P, and then you're just going to use the number of moles, the volume, the temperature, etc. for that individual gas, and that'll give you the pressure of that individual gas. So for a multi-component gas mixture, we can do this. Let's say we have a gas that's got 3 components to it, right? The sum of the partial pressures of the components equals the total pressure. So here I have the pressure of A using the ideal gas law, that then goes here. Pressure of B using the ideal gas law, that then goes here. Pressure of C using the ideal gas law, that then goes here. So the total pressure, as we saw in the previous slide, is the pressure of gas A, pressure of gas B, pressure of gas C, all added together. Now, it is important to note that when you see this written elsewhere, you're probably not going to see ABC. It's usually, because that's the generic notation. So what you're usually going to see is like, P of oxygen, O2, plus P of nitrogen, N2, plus P of carbon dioxide, CO2. So you'll usually see the gas, the identification of the gas in here as A, B, or C. So we know, again, from the previous slide, that I can substitute or rearrange the ideal gas law to get pressure for each one using N times RT over V. Now, Whenever I have a mixture of gases, it's one single container. Well, that container has a temperature and a volume. So what I can do is actually pull RT over V out to simplify the equation. And that leaves me with number of moles of A plus number of moles of B plus number of moles of C, which means my total number of moles times RT over V will give me my total pressure. So this is why we can treat mixtures like pure gas in some situations. Now, we can also do this math using what we call the mole fraction. So the ratio of the partial pressure of a gas to the total pressure of the gas is equal to the mole fraction. So the number of moles of that particular gas divided by the number of moles total, right? So our mole fraction we can use to help figure out whatever the partial pressure of a gas is. So the number of moles of a component in a mixture divided by the total number of moles is the mole fraction. And it is equal to this, the pressure of that gas over the total pressure. So I can figure out the pressure of any gas by taking the mole fraction. Let's say oxygen makes up 70% of the mixture. Well, then 70% times the total pressure gives me the pressure of oxygen. So what does that look like? The partial pressure of a component in a gaseous mixture is its mole fraction multiplied by the total pressure. So an example of a kind of problem that you're going to see is nitrogen has a 78% composition of air. Find its partial pressure. So if I know that 78% or 0.78 of air is from nitrogen, then I know that 0.78 of its pressure is from nitrogen. So assuming 1 atmosphere, 0.78, that's our 78%, times 1 atmosphere gives me 0.78 atmospheres. So this would be the partial pressure of our nitrogen. So if I do that for the 3 major components of air, we've got the partial pressure of nitrogen, did it again for oxygen, partial pressure of oxygen, partial pressure of argon gives me 1 total atmosphere, which I already knew, but this is just confirming that this works, right? So why do we care about these things? One big example of where partial pressures matter is when we're talking about deep sea diving. So when a diver breathes compressed air, the pressure of that air means we have higher pressure of oxygen. So the abnormally high partial pressure of oxygen in your lungs that you're breathing in leads to elevated oxygen in your body tissues, including in your brain. So we have regular air at the surface has 21% oxygen or 0.21 atmospheres of pressure. Well, the further down you go, the greater the pressure is of the oxygen. So once we get beyond 1 to nearly 1.5, this is sort of the end of the safe zone. And then when you get further, you get what we call oxygen toxicity. And this is what we run into whenever it literally like screws with your body and your brain and like makes you sick, makes you drunk, makes you make bad decisions. So if you ever hear about somebody getting narked whenever they are scuba diving, this is kind of what we're running into, is too much oxygen in the brain, and it's actually like befuddling you while you're diving. So this is an application of where our partial pressure is kind of really important. So let's talk about Dalton's law. So we said that Dalton's law of partial pressure is where our total is equal to the sum of the partial pressures, right? According to the kinetic molecular theory, the particles have negligible size and do not interact. Particles that have different masses have the same average kinetic energy at any given temperature. So, because our average kinetic energy is the same for all of them, the total pressure of our collisions is the same. So that's why even though we have these particles that vary in size, so one argon atom versus like a CO2 molecule, totally different in size and mass, because they're at the same temperature, because we have a container that's at a temperature, the average kinetic energy is going to be the same among them, and so the total pressure from the collisions will be the same, even if they have different masses. So, when we are observing gases, how do we do that? Well, we can collect them. So, usually, the way that this will be done in a lab and the way that we do it in Chem 112 is collecting them by displacing water from a container. So, the problem with that, and it's a problem that we can easily deal with, but the problem with that is because water evaporates, there's also going to be water vapor in the gas. So, if I'm collecting oxygen, for example, it's not going to be pure oxygen. There will be some water vapor just because by its nature water evaporates, right? So when we do that gas collection, we just have to take into consideration the water vapor's partial pressure. So the partial pressure of water is what we call the vapor pressure. It is dependent on temperature. That is a reference value that I will show you a table on the next slide. So this is not something that you need to memorize, but it is something you have to account for. If you collect a gas sample with a total pressure of 758.2 millimeters of mercury at 25 degrees Celsius, well, the partial pressure of water vapor is 23.78 millimeters of mercury at that temperature. So that means that the partial pressure of your gas that you collected plus the partial pressure of your water has to equal that total amount, that 758.2. So the partial pressure of your dry gas, meaning total minus the pressure of the water vapor, is 734.4. So again, here is a reference table for you. 25 degrees Celsius, here was that partial pressure of water there. And so this is what that looks like. We basically fill up this container with water and then have this gas producing reaction over here. As the gas molecules push through this tube and up into this container, it's going to bubble up, and there's not going to be space for all of that gas plus all of the water that was in there. So it pushes some of the water out, and we collect this gas here. In this case, it's hydrogen gas. In the Chem 112 lab, it's going to be oxygen. But you're going to collect that here, and you'll notice here it's pure hydrogen. The two little two little white circles here. It's pure hydrogen. But then by the time we get here, there's the occasional water molecule mixed in. So that's not a problem. We just have to account for it in our math. So that is it about Dalton's law of partial pressures.